All right,
Let me get used to
let's
that.
take a look at the breadth first traversal of this. Now, the breadth first traversal is going to be where we used a stack essentially, or recursion when we did the depth first. With the breadth first, we're going to do a cube. And it's kind of similar.
That's when she'll get you to sleep. That's my job for a good portion of my life.
So we'll use the same graph, but in this case, what we'll do is we'll set up a cube. So here's the front of the cube, here's the rear of the cube, and what we do is we will remove a vertex from the front of the cube. We start by saying that the first one's processed, so we'll keep the same kind of array. And so what we'll do is we'll say 0 is processed, and then we'll add them to the cube, and away we go. What we do now is we remove a vertex from the front of the cube. For each unmarked neighbor, process it, mark it, and then place it in the cube. So what we'll do is we'll take 0 off of the cube, and now what happens for 0, we look at him and we go, oh, 4 is one of his neighbors. So we'll mark it and we'll put a 4 on the cube. And then we'll go 1 is one of his neighbors. So we'll mark it, put that on the cube. And that's pretty much it. Then what happens is we pull the front guy off the cube, which is 4. Now we look at 4. 4 doesn't have any neighbors, so 4 is pretty much gone. Then we pull the 1 off of the cube. So now we look at the 1. He's got a neighbor 3. So we'll do that, and then we'll put the 3 onto the cube. And then we'll look at what other does he have. That's it. So now we pull the 3 off of here. 3 has a neighbor 6, which will visit, and then got a neighbor 5 that will visit. And then so we put the 6 here and 5 here. We pull the 6 off. 6 has 1 as a neighbor, but 1's already been visited. And so he's done. We pull 5 off. 5 has no neighbors. Cube's empty. We're done. Pretty straightforward. This one, you need the cube. You can't do this one recursively. We could, but it's kind of weird. That's it for breadth first. Now, the last thing we want to do is talk about Dijkstra's shortest path algorithm. Now, one of the things that changes with this is that it's no longer whether or not you have an edge. It's how much does that edge cost. Because one of the things that we want is the least cost while we're doing this. So let's draw a new graph. And this new graph is going to have some costs associated with it.
This is for the Dijkstra?
Yep, Dijkstra's shortest path. 0, B1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. And from here to here, this costs 2. From here to here, this costs 6. From here to here, this costs 9. From here to here, this costs 3. From here to here, this costs 3. From here to here, this costs 7. From here to here, this costs 8. And from here to here, this costs 15. from here to here is cost 1. So what do we got? 2, 9, 6, 15, 8, 1, 7, 3, 3. All right, here's our graph.
What page are you looking at?
This is page 761. All right, so this is a weighted graph. Now what we want to do is we want to determine what's the least cost to get from one place to another. Now, one of the things to keep in mind with the shortest path algorithm is that it actually doesn't give you the path, it gives you the cheapest cost. You can determine the path if you wanted to on the way through, but what we're just about is what's the cheapest cost to get from any vertex to any other vertex. What we're going to do is we're going to take an array, and in here what we're going to do is we're going to say this is 0, 1, 2, 3, 4, 5. The cost to 0, if we're starting at 0, is 0, because we're already there. And now what happens is we're going to have to, one way to think about this is that it's, you ever heard that old adage that says, go as far as you can see, once you get there you'll be able to see further? That's what this whole algorithm is all about. When we first start out, we know that as far as 0 is concerned, we can get there for a cost of 0. But for all the other guys, when we first start out, they're infinite cost. And we're going to take a look at that and see what happens. We're going to modify this each time as we go through. So what we'll do is fill in the distance array with infinities at every location, with the exception of start, which will give us 0. Initialize a set of vertices called allowed vertices to be the empty set. So we need something called allowed vertices. And initially it's just the empty set. Be the empty set. Throughout the algorithm, a permitted path is a path that starts at the start vertex and in which each vertex on the path, except perhaps the final vertex, is in the set of allowed vertices. The final vertex on a permitted path does not need to be in the set of allowed vertices. At this point, allowed vertices is the empty set, so the only permitted path is the empty path without any edges. This empty path does contain one vertex, the start vertex, but since this vertex is the final vertex on the path, blah, blah, blah. Third step is a loop. Each time through the loop, we will add one more vertex to allowed vertices and then update the distance array. So all allowed vertices may appear on paths. Here we go. Loop. Let next be the closest vertex to the start vertex that is not yet in the set of allowed vertices. If several vertices are equally close, you can arbitrarily choose one. So in this case, from V0, the closest one to it as far as weight is concerned is which one? Yeah. The closest neighbor? V1. So, add the vertex next to the set of allowed vertices. V1. All right? Add the vertex next to the set. Revise the distance array so the new vertex next may appear on permitted paths. So what happens is, first time through, we're going to know that this guy is of cost 2. If you think about it, the lowest number that's directly connected to you, there's no way you're going to get there any cheaper. So that's basically what we're doing here. So now, we'll go back around. Revise the distance array so the new vertex may appear on permitted paths. And we loop around and around. It says loop's computation hinges on the condition written just before 3a. That the list is set actually contains allowed size -1 that are closest to the start. Blah, blah, blah. How to choose the next vertex in step 3, blah, 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 blah. All right, so what happens here is step 3a, the step must in which the unallowed vertices closest to the start. There's a simple rule for choosing this vertex. we'll always choose the unallowed vertex that has the smallest current value in the distance array. If several vertices have equally small distances, then we may choose any of them. All right. For example, suppose we reach step 3. Okay, blah, blah, blah. We just repeat this now. So we've gotten to 2. So now what happens? Which one's closest after that would be 9, would V5 would be 9. So we set this guy to 9, and then we set V5 in the set of allowed vertices. And we don't have any information that changes any of these guys. So now what happens is we go to the next, and I've looked at several different implementations of this, and it's kind of weird when you think about what's going on. It says, so we'll add the next one, which is the closest one to the start. What's really interesting is if you think about the closest one to the start, it isn't necessarily this one. Because if you think about it, if we go to V1 and then we take a look at what's the next, we can get to V5 for 6 or V2 for 8 at that point in time. What this is going to be is it's iterative refinement. We're going to pick a path, we're going to take that path, and then we're going to refine this as we go through it. So, let me see if they have a, yeah, here we go. All right, initialize the distance array to contain infinity except for the first. All right. Let next be the closest vertex to the start vertex, which is not yet in the set of allowed vertices. Closest is the definition means that it has the least cost. Add the vertex to the next. Revise the distance array so the new vertex may appear on the permitted paths. Start with 0, go to down on the allowed vertex, and there's an edge. Sum equals distance of next plus the weight of the edge from next to V. So what you can think of. So first thing we do is we get the 2, and then we put the 9 out here, and that adds it to here. So now we've done the 9, and then what we'll do is we'll loop through here. And the next time through, what we'll do is the second time we enter the main loop, the value of next is set to vertex 1, which is the closest one because we've done everything that we could do from the start. So now we go to the closest one to us, which would be this guy here, number 1. And then we repeat this process. What's going to happen now is we take a look at what's the closest one from there, which is going to be 5, which we're going to change now because we're going to add, V1 is already on here. We're going to add V5, he's already here, but now by going to V1, which where we are, we can see that 2 plus 6 beats what used to be there. So that goes there. That becomes an 8. Now we can also go at this point in time that we can pick the closest one of his kids. We could go to V5 and just say, where do we go from there? And if we do, he's going to take us to V4, it's going to take us, or what we can do is we can go to V2, which is going to be a cost of 10, right? So because it's 2 to get to V1, then this becomes a cost of 10, and we add V2 to this list. Now we can also go to V3, which is going to be a really big number, right? Which is going to be the cost of this guy plus 15. So this one's going to be 17. And then what we do is we go back through and we make sure that we don't have to change any of these based on what we know, which in this case, we don't. But now we can go to the next least expensive one in his case, and it would probably be that we would go to this guy, because he's the least cost at that point in time. He can go to V4. Actually, we have to add V3 here too. V3 is allowed and V4 is allowed. So we can go to V4 for the cost of whatever it costs to get to V5 plus 3. This becomes an 11 at this point in time. And what else can we update? Not much at that point in time. We should have 2, 10, 17, 11, and 8. Now, we still keep going, because if you look at this, we still can update things by going to the least cost of the kids that are remaining from V5. That takes us to V4. At V4, we can then go from V4 to V3 at the cost of V4 plus 3. So we can update this one to V14. And then we can V1, V5, 1, 2, 3, 4, 5. We'll repeat this process over and over again until we're done. Now what's interesting though is that we've gone to from 4 there. Now from 4 we could also go to V2 for the cost of V4, which is 4 plus 7, which is not going to beat that cost. So now what we have to do is each time go back through this, find out what's the lowest cost value, go there and see where you can go from there. Now 8 was the lowest cost value, 10 is the lowest cost value. If we go to 10, which is V2, that's going to take us from V2 to V3. It's only going to cost us 1 more, which is 11. So basically what you're doing is going to the lowest cost value and then recalculate your distances from there. Go to the lowest cost value, go as far as you can see with the lowest cost, and then once you get there, you'll see more. And you just iteratively repeat that. I'm not going to make you implement this guy. 2, 10, 11, 11, 8. Yeah, that's pretty much it at that point in time. I'm not going to make you implement this, but make sure you understand the algorithm in here, because I'm going to show you a graph and say, give me the shortest paths from these 2 vertices. That's what you're going to see on the final. Now, I met Dijkstra a long time ago, 1984. I worked at a company called Data General, and he invented the language Algol. How many people have ever heard of the language Algol? Yeah, not surprised. It's a predecessor to like PL1 and a lot of modern programming languages come from Algol. And I worked at Data General, and they had a language called DGL, which was Data General's Algol. And they wanted to do something that was kind of weird, is they wanted to do, in programming languages, you have L values and R values. You ever heard of L values and R values? If you look at an equals sign, right? Anything over here is an L value. Anything over here is an R value. So an L value is something you assign into, and R value is what you assign to it. Data General decided they wanted to be able to do something like put a substring here, let's say down to 2, down to 3, or whatever, and assign something like this into it. So he wanted a statement so you could assign it to a substring. And Algol didn't permit that, but Data General wanted that in their Algol language. So Dijkstra said, no way. So they invited him to come so they could talk about it to see if they could change his mind. And that's why it's called DGL, because it used to be called DG Algol. But when Dijkstra got there and the people from DG said, we want to do this. And he said, no, you can't do that. It violates the language. I won't let you call it Algol if you do that. So they wanted to keep it. He said you can't call it Algol, so they changed it to DGL. And as part of the deal, he gave a speech to all of engineering about concepts of computer science and that kind of stuff. And they had a raffle. To whoever won the raffle would go out to dinner, and I won. So I had dinner with Dijkstra, which was kind of cool. It's like if you're a computer nerd, he's one of those guys that you would really like to have had dinner with. I have had dinner with him, which was really kind of cool. But yeah, some amazing algorithms came out of that. Just have to remember, this stuff all comes from Amsterdam, where weed's been legal for a long time. Okay?
The 7 conifers.
Yeah. He was at the University of Amsterdam.
Oh, okay. I meant that.
But yeah, brilliant guy. All right.
Of course he did. You're final.
Done. All right. Couple things here.
That's fine.
Yeah, this is fine.
I thought
You
it
said it
was-
right.
10 minutes.
Oh my god.
I thought
You
it
got the
was
graph
one
stuff
more.
down,
I was
right?
like,
Yeah,
I thought
yeah,
it was
yeah. Okay,
gonna
good.
be
Because
What
he
do we
asked.
have to know for the Dijkstrom's algorithm?
Yeah, I'll do that.
I'll do it.
Just how to do it?
Yep, it's in the book.
Let's take one.
Oh, lovely.
That'd be nice.
You don't want to collaborate?
Let's take one final.
Page 71.
Yeah, just left it in a couple days. It's just a project. Oh yeah, I submitted on time, but it's just like
This is where you do your course evaluations. You have to log in with your BUID, and you can do that. It's yeah, course eval. All right. Before we get to the final exam topics, here's an optional homework for you. Note, this homework is optional. See that big word, optional?
Would this help in final exam?
Will it help with the final exam? No. Man, you have a one-track mind. Hey, how about the red sacks? Will this help with the final exam? So, what you need to do for this is choose either edge lists or adjacency matrices to, you're going to add a method to a graph class. And I'm going to tell you right now, adjacency matrix, okay? Just telling you. You're going to want to use that one. And what you need to do is write a method that allows the deletion of a vertex from a graph. Not an edge, a vertex. So the process of deleting a vertex, write a method that allows the deletion of a vertex from a graph. In deleting the vertex, the method should not only delete the vertex, but every edge that has the vertex as a source or a target. Yeah, because once you delete that vertex, nobody can point at it anymore, and it shouldn't be pointing off at anybody anymore. So turn in the code for this, as well as output demonstrating the successful deletion of a vertex, and all associated source and target edges that refer to the vertex. So it's worth 2 points. Like I said, if you do this with an adjacency matrix, I mean, this shouldn't take you more than 15, 20 minutes. It's pretty straightforward. Just search for the vertex, search for the edges, delete them all, and you're pretty much done. Yeah. What's that?
We can just search for them and delete them all.
Yep.
So how the output will look like?
That's called.
You'll just print out the vertex, probably with the print string that you're going to steal from my code anyways, and it'll just show that there are no longer any things that report to it, that point to it.
Yeah.
All right, what's on the final exam?
Everything.
It is comprehensive. Sorry. But it's 30% before the midterm, 70% after.
What's the makeup of the stuff? It's mostly after the.
Oh, okay.
I think we didn't do that much after the midterm.
Yeah, we didn't do that much after the midterm.
No, the midterm was like not in the middle.
Yeah, it was.
It was literally in the middle.
Yeah, pretty much. When you see this list, you're going to go, oh, wow, we did all that after that?
And then we'll recurse the gods.
Yeah, recursion was after the midterm. So we're binary trees, searching, sorting, hashing, all that stuff. All right. So, same format as the midterm. 12 questions, answer 10. There'll be 3 programming questions. Scratch paper will be provided. 70% post-midterm, 30% pre. The entire book is covered. I mean, when I closed this book after talking about graphs, there was only like the index was all that was left in the book. So we've covered the entire book. So anything that is in bold but doesn't have any bullets underneath it and the topics, that's stuff that's pre-midterm. So after the midterm, we did binary trees. Make sure you understand the difference between complete trees and full trees, And make sure you understand your traversals, which you should, complements of the last programming assignment. There's a couple pages in your book that have a complete definition of all the terms that are associated with trees. Make sure you bring that, because that's going to be really helpful. Make sure you can do the traversals. And by do them, I'm going to give you a binary tree that's filled in with numbers. And I'm going to say, I want the list of the nodes in pre-order, post-order, and in order. Hashing tables, open address hashing, chained hashing, quadratic probing, linear probing. Make sure you understand that. And now look, are you bringing these notes with you to the final exam? Are you?
Yeah.
Yes.
Bucket. Write it down. Yeah, bucket. What's a bucket as far as a hash table is concerned?
Oh.
What is it?
Isn't it a slot in the array?
Yeah, in a table. It's a slot in the table.
It
But
could hold a chain, or it could hold an object or an address.
I'm telling you this because I'm doing you a solid here, okay? Because there will be a question on there that's going to say something like, "Hey, what do you call the entries in a hash table?" It's not locations. It's not any of that crap. It's bucket. I'm helping you out here. Take notes. All right. Sorting algorithms. Make sure you can implement a bubble sort, a selection sort, and an insertion sort. And you have an understanding of how the recursive sorts work. I'm not going to ask you to implement either of them. I may ask you to implement part of them.
The base case?
Yeah. Like, I might ask you to implement the merge for a merge sort or something like that. I won't ask you to do the partition function because that's a bear. Recursion. Make sure you understand factorial, Fibonacci. Make sure you understand asterisks. Maybe even printing strings of numbers with recursion. You know, all the way up, then all the way back down, that kind of thing. Make sure you understand that. Hey, look, here's tonight. Directed graphs, undirected graphs, edge lists, adjacency matrices, Dijkstra's algorithm, breadth first searches, and depth first searches. Son of a gun, we covered all of that stuff tonight. We're good. It's good to be good. Searching, linear or serial searching, it's a for loop. Binary searching, make sure you understand both the recursive and the iterative binary search. General programming, there will not be any determining output. You guys didn't seem awfully pleased with that one with the midterms, so we'll remove that one from the final exam. Not much with syntax at all, and probably nothing with static data. So, there you have it.
What do you mean by static data?
Inside of a class, static data.
Now it's back on the final. Thanks a lot.
Yep, now I gotta put it back on there.
No, I thought you were referring to something else.
What? They got it back on.
So, look, this is the last time I get to talk to you. Because next time you'll come and be grumpy as hell, you'll take an exam and leave. Thank you. I learn something every time I teach this class.
What did you learn this time?
What did I learn? Well, shut the camera off. I mean, and all the way up through a PhD, this class is foundational. And that's why they say, hey, you want to teach introductory? Not so much. I want to teach data structures. I have taught this course, probably 35 times. And it never gets dull.
And this is the
It
best
never
class.
gets old.
You teach any other classes?
I do. I mean, I've taught artificial intelligence, machine learning, advanced operating system theory, data forensics, a whole bunch of different stuff.
Now or back
Nah.
in the past?
In the summer, I'm teaching this course again. Hopefully, I don't see any of you there.
Well, no, if you just pass us, then.
In the fall, I'm teaching this course again. I hope I don't see any of you there either. But yeah, I sometimes I'll teach 2 courses a semester, but it's hard. I'm in a startup that's actually starting to take off. So I mean, we're we're doing a few $1,000,000 a year in business now, and there's only a handful of us, so that's a lot of work. So one course I can do, 2 is tough. But thank you very much. I hope you got something out of this. I hope you don't hit me too hard for not getting your assignments back as quick as I probably should have, but that's okay, I understand. But you guys are great. You guys will be fine. Just don't overthink it. A lot of you guys tend to do that. Typically, software engineering is all about the KISS principle. Keep it simple, stupid. Yeah. If typically the most elegant answer is the simplest. So if you, and remember, now that you've seen the midterm, remember on the final exam, I'm not going to ask you to write some code that's going to take the back of every sheet of paper. If it does, you missed something, okay? Most of these things are going to be 10, 12, maybe 20 lines max. And you'll do fine. And for those of you who have sent me requests to connect on LinkedIn, after the final I will answer. I don't do it when you're in class. So, but I do accept those. And if you guys are looking for letters of recommendation or anything like that, and I can help, let me know. Okay? I want you guys all to do well. It's important to me. Am I hiring? Not at the moment. Probably in about 4 months. Yeah, because right now we're just getting to the point where we're breaking even all the time, every month now.
What do you sell?
We sell a product that you insert into your pipes at home, and if you're not home and your water starts running, it shuts it off for you.
So it's like an Internet of Things?
Yeah.
Oh, cool.
So it uses the MQTT protocol, stores all your data up in the cloud, gives you accurate readings of how much water you're using, gives you the ability to shut your water off if you want to, but it also, records how much is going on. If you're not home and your water starts flowing, that means your pipes are probably leaking, and we send you a message first, say, hey, your water's flowing, and then we shut it off. And it also shuts it off if it gets too cold, so if your pipes don't freeze, that kind of stuff. So it's a pretty cool product, actually. We have sold thousands of them.
Give us a discount?
Your insurance company will pay for it, probably. So your insurance company will give you a discount every year that will allow you to recoup the investment in probably 1 to 2 years.
Well,
How do you install that?
You have a plumber usually. We have a version that just monitors, but if you want the one that shuts off, typically you have a plumber come and do it. It costs like $600, something like that. And the thing is, your insurance company will give you a decent deduction on your home insurance, like 8%, that type of deal, 5 to 8%. And well, for insurance companies, water damage is the biggest claim. In the U.S. last year, I think it was $11 billion in water claims, and in Europe, it's bigger. So this is something that insurance companies like a lot. We're partnering with insurance companies like mad right now, so it's kind of cool. I think this one will actually go somewhere. WaterHeroInc.com. WaterHeroInc.com. Check it out. Nice smiling mug is on that thing. Thanks again, folks. And good luck on the final.
Thank you.
And see you around. Say hi. I won't remember your name, but say hi.